So let's go back to principal component analysis. We're talking about how to use everything that we have derived thus far to design a very powerful algorithm that we'll be using throughout the course. You'll be using this throughout your applications or uses of machine learning. Super popular, super useful. So let's get back to that. So let's remember where we were at. Let's review very quickly. We've computed the covariance matrix that, remember, specifies the correlations of the data. So we have our covariance matrix sigma x, and from that sigma x we can do an eigenvalue decomposition. So we have the matrix V, whose columns are the eigenvectors of sigma x, and capital lambda, it's a diagonal matrix of corresponding eigenvalues. So V, I'm going to say, is a small v1, still vectors, of course, the eigenvectors. These are the columns of capital V, which are the eigenvectors. So V1 through Vp, lambda, the diagonal matrix of corresponding eigenvalues. And remember that we've assumed that lambda 1 is the largest one, lambda p is the smallest one. So if the rank of sigma x, let's call it q, is smaller than p, the number of dimensions, then that means that some of the eigenvalues are equal to 0, right? So remember back to the correlations and the feature space that we're talking about. That means that there's no variance about that dimension, right? Represented by those eigenvectors. That means that we can obviously eliminate those eigenvectors from our representations because they don't represent anything. So I can actually construct a new matrix. Oops, hold on. Sigma x, let's call it sigma x sub q, that represents the exact same covariance matrix of the data, but only in q dimensions instead of p dimensions. And that can be easily given by capital VQ transpose sigma x capital VQ, where VQ has the first q eigenvectors that we have obtained here in my capital V, right? And that's because lambda 1 is larger or equal than lambda 2, larger or equal that all the way to VQ, which is larger than lambda q minus 1, which is equal to all the other ones up to p, which are equal to 0. Okay? Because the rank of sigma x specified those eigenvalues have to be 0. So this new matrix is also symmetric and now positive defined. Remember, sigma x may be positive semi-defined, but this is defined because we've eliminated all the eigenvalues that are equal to 0. Among other things, this means that sigma x sub q has an inverse, since all positive definite matrices do, obviously. It also means that we can apply any other projection defined by any non-singular matrix W, and the resulting matrix will still be positive defined, right? So I can write this as a result, if you will. I can say that if I have a matrix M defined in the space of Q by Q dimensions, right? Any matrix M that is positive defined, and W, which is a matrix of Q by K, with K smaller than Q, And therefore, I'm going to say, and WB of rank K, right? Then it follows that the projection of M onto W, from M, onto W is also positive defined. So a couple things that are worth mentioning. Obviously, this result implies that, or states, in other words, it states that when a matrix M is positive defined, then all its diagonal entries are positive. That's just by definition. And that any principal submatrix, a principal submatrix is a submatrix of M where you eliminate the M columns and M rows, the corresponding columns and rows from the original matrix, right? That any submatrix, principal submatrix of M is also positive defined. All right, what else? So let's apply this to our data. So we have our data, which is given by x1 through xn. These are our n observations or samples that we have been using. We can now also represent those samples in any subspace of the original space, right? So I can use, say, VR. I'm going to define it with V1 through VR, right? The first R eigenvectors of my covariance matrix. And now I can compute any xi that I have here is going to be equal to VR transpose xi, right? So I can project this onto this, and I'm going to call this new one, let's call it maybe VR sub I. Okay, how about that? Right? Now R has to be up here with R smaller or equal than Q, right? Yes?
I'm sorry, you have X, I couldn't, what from the subscript you wrote, is that XRI?
Yep.
Oh, R, okay.
Yep, you can call it, if you prefer, you can say X hat sub I, if that's meant. It's just whatever notation works for you, honestly. All right, so this right here is called the principal component space, or PCA space, which is given by the R eigenvectors. Yes, question?
The result, it says the N matrix is R by R matrix.
The N matrix is? Oh, K by K, right? Is that what you mean?
Yeah.
Right here? Yep, thank you. So this is what the PCA space is. It's defined by the first R principal components or eigenvectors. When you hear principal components, it just means eigenvectors. Principal components, PCs, or the eigenvectors of sigma x, our covariance matrix. okay? And that basically defines our PCA space. Now, PCA, they're actually, by the way, just to give you a historical perspective of this, PCA is nothing else, as we have derived it here, than linear least squares. We spent like maybe a third or more of a third, almost 2/3 of the image processing class describing linear least squares. Well, that's just another application that we saw in image processing, right? The principal component analysis, it's nothing else than linear least squares, which was derived first by Gauss, right? Famous mathematician Gauss. That's where it comes from. Now, the derivations of the least squares apply to defining PCA are due to, if I can remember, Carl Persson. That's right. Carl Persson, who is the other famous mathematician of whom you have heard the Persson correlation, right? Same guy. He was a student of Galton. Do you remember Galton? Galton was the person that described the wisdom of the crowd by the convergence to the mean, right? Remember all that? Okay. So same people. So this goes back, I think, Persson, when he defined principal components analysis, that was probably about the turn of the century, if I remember correctly, 1901. So method has been around for a while, extremely useful to this day. And the question is, why is it so important? What are the properties of PCA that make it so relevant? So let's take a quick look at this. All right, so perhaps one of the most important reasons why PCA is still so relevant today is because of the following result. Let sigma x, I'm going to call this sigma x tilde, equal to W transpose sigma x W, where W is a P by Q matrix defining the orthonormal projection that we have defined there. Oops, the orthonormal this projection that we have defined right here, right? This orthonormal projection. X tilde equal W transpose X. That's nothing else than projecting orthographically, right, onto a subspace. And Q is an integer between 0 and P. Sigma X obviously is the covariance matrix of the data defined in the space RP of P dimensions as we have been using it. X is a vector obviously, with X is a vector obviously in RP as well. Then the trace of sigma x tilde, that is the trace of sigma x tilde, is maximized when W is equal to VQ. Is that what we said? Yep, VQ. Okay, let's unpack this, shall we? What that means is that if I consider any orthographic or orthonormal projection, right, that means that I start in some p-dimensional space, RP, and I now identify a subspace, right? Maybe this one here. And I project all the data points that I have orthographically to that subspace. Okay? That the optimal matrix or orthographic projection is going to be given by the eigenvectors of the covariance matrix, aka the PCA space, right? If my criterion to evaluate this is maximizing the trace of sigma x, the projection of sigma x. What's a trace of a matrix? Anyone can tell me what the trace of a matrix is? It's the sum of the diagonal elements. Very good, excellent. So the sum, we'll say P from 1 to P. Let me call them small m II, meaning the ith row, ith column, right? So the diagonal elements. Very good. But the trace of a matrix is also equal to something else. Anyone knows this? What's that? The sum of eigenvalues. Very good. Actually, the trace of a matrix is also equal to the sum of our eigenvalues. And what is the way that we know to maximize the sum of eigenvalues? By eliminating the smallest possible eigenvalues. And what approach does this? PCA does this, right? It keeps all the eigenvectors associated to the largest eigenvalues. So obviously there's no other combination of basis vectors I could select that is going to give me a bigger, larger value for the trace. So just because of the definition of the trace, that holds. That means that when I project my data onto the subspace defined by the principal components, I keep most of the variance of the data, right? Regardless of the value of R. Now, if R is equal to Q, Q the rank of sigma x, then I have absolutely no loss. But if R is smaller than Q, then I have loss, but it's the smallest amount of loss I could have if I worry about or I care about the variance defined by the eigenvalues, okay? Now, sometimes you will also see, so you'll see this all the time, that people will say, we use PCA because we want to keep most of the variance of the data, right? Some other people will actually say that they want to keep most of the energy of the data. And that sounds really weird. And what they mean by this is that if you remember, if we go back to the Stir decomposition, right? Remember that we had our matrix, in this case sigma x, it's equal to V capital lambda V transpose, right? And that I can express it, or I can write it down as, let's see, this would be lambda 1 times V1 transpose plus lambda 2 V2 transpose all the way to lambda P VP transpose, right? That's the same thing, correct? Now, this that comes from the Stir decomposition is also, in fact, the same or the same equation that you have when you describe the spectral decomposition of a matrix, right? And because of that spectral decomposition that we show here, people sometimes say, well, if I eliminate the eigenvectors associated to the smallest eigenvalues, I keep most of the energy of that spectrum. Okay? So that's where it comes from. So you will see these two things being used interchangeably. All right. Now, next, this is the key question that comes next. how do I determine the value of R? Because up to now, everything has been very formal, right? We have said, okay, we start with this very mild hypothesis, right? And from here, we've derived every single result formally, and this is optimal with respect to that criterion, right? The least squares criterion gives this algorithm, and this is optimal with respect to the least squares criterion. Fine. Everything is very formal. But for the small detail, we don't know what R is, right? If R is equal to Q, yes, we keep all of the variance, and therefore we have no loss. But generally in practice, you want R to be much smaller than Q, right? Because you will see in most of the applications that you're going to be working, not all of them, but in most of the applications you're going to be working in machine learning, P, the original space, is going to be huge. It's going to be in the many thousands or even millions, right? So Q may actually reduce you to maybe hundreds of thousands, maybe tens of thousands if you're lucky, right? But you may want to go lower because you don't have enough data, things that we'll talk about. The question is, how am I going to determine the value of R? And unfortunately, there is no right answer here. And we have to use heuristics. So what I can do is that I want to keep, say, SQ percent, or SR rather, percent of the variance, where SR is going to be defined by 100 times the sum of the eigenvalues that I use, so 1 through R, divided by the trace of sigma x that you already know is the sum of all the eigenvalues, right? Okay? So it gives you the percentage of variance that you keep in the data, of the data, when you project to the PCA space. Now, what is the percentage that you want to keep? In practice, you want something between 70% and 90%. Something between 70 and 90% of the variance. That's what you want to keep. Now, that's not the perfect rule of thumb, right? Sometimes you may want to keep 99% of the data, right? Excuse me, 99% of the variance of the data, right? How are you going to determine that percentage? Generally speaking, again, this is very broad, but generally speaking, if you need a very large number of eigenvectors, so R is very large, to get 70% of the variance, then 70 is probably a good number for you. On the other hand, if with very few eigenvectors, so R very small, you get 90% of the data, then you definitely want 90% of the data, right? There is no right solution here, but those are broad suggestions that people follow. Now, you will see all the time, and we will be referring to this when we talk about other more advanced algorithms in machine learning, that people will say, we first projected our feature space into the PCA subspace, or the PCA space, meaning the same thing. And to do so, we kept X% of the data, and that's what they mean, okay? Now, when you eliminate some variance of the data, you do so, in principle, for two reasons. Number one, because the original feature space is too large for you to work with. Okay? Number two, because you assume that the eigenvectors with a small eigenvalues correspond to the noise in the data. Right? So, if I collect data and I observe that for some specific dimensions of my feature space there are small variations, right? I can interpret those small variations as noise, additive noise that has been added to my data. This is somewhat true in some cases, but it's not generally true. What usually happens is that you get rid of the high frequencies of your data. It might be a good thing or a bad thing, right? So for example, as you will see in your first project, when you project images of objects or faces onto the PCA space and then you reconstruct them, they look like almost like blurred images of the original image, right? Of the original image of the object. And that's because you have eliminated the high frequencies of the image when you were doing this. We can also interpret the results that we have derived here for PCA geometrically. PCA is a projection that minimizes the distortion of the shape, so to speak, and I have to use quotation marks again, of the shape of our data. So remember that I start here in my feature space. I have a certain number of points, right? Something like this. And then I compute my PCA. So let's say that I start in R2, and my PCA space is of one dimension, so R1. Okay? And I project orthographically all my data points onto that one dimension. That projection is the one that keeps the structure, the original structure or shape of the data most intact. Okay? What do we mean by this? Let's be more formal about this. What we mean is that if we define a specific norm to measure the distance or the structure of that data in the original space, and the same norm to define the shape or structure of the data in the reduced space, that norm is the minimum value, or that difference of norms is the minimum we can have. Usually, what we're going to use to do that is we're going to use the Frobenius norm. So just as a reminder, the Frobenius norm is of a matrix. I'm going to write it as F, right, in my norm, in the computation of my norm. It's nothing else than the sum of every element of my matrix squared, okay, over Oi over Oj, and then the square root of that, right? Now that equation may or should feel familiar. This is the exact same equation as the Euclidean norm for vectors, right, the true norm. But for matrices, the true norm, it's a different norm we saw in image processing. So what we want to do, we want to find the minimum, right, the minimum projection M that minimizes sigma x minus M, right? That's our goal. We want to find this. Now, how are we going to do that? Well, remember, if M is given by this equation here, you see this equation, right? So I can define M as lambda 1, V1 transpose, all the way to lambda Q, or R, VR transpose. Okay, so if we define this same as this, but up to VR only, right, then this is going to be equal to lambda R plus 1 square plus lambda P square root, right? And then, of course, we know, again, that the smallest we can ever have is exactly this number, right? There's no other orthographic projection that is going to give me a smaller number than this, right? So again, we keep getting the same result over and over again, because obviously we're doing the same thing. So we can summarize this in another result. We can say, let's start with, let capital X be the mean normalized data. So I have x1 minus mu, x1 minus mu, okay? And this is a P by N matrix, right? That defines our N samples, each sample in RP. Mu, the sample mean here. And now we define our X tilde as the projection of our data onto some orthographic or some subspace. We orthographically project our data onto subspace, where M, it's a P by Q orthonormal projection matrix. Then the Frobenius norm of X transpose X minus X tilde transpose X tilde is minimized when M is equal to VR. Okay? Or VQ. Did I use Q or R? I use Q this time. I use Q. Okay. So change this to R or this to Q. I'm going to change this one. Okay. Okay? That's the power of PCA. PCA, it's optimal with regard to linear least squares, and it optimizes all these different criteria. Okay? Now I see, it's just a large class. I see some people struggling to see. It's all in the notes that are posted online or will be posted online. You don't have to copy every single result. They're all listed online. All right, so let's see how we can use this to design, or rather than to design, to how can we use this algorithm to do things, useful things with our data. Obviously, PCA, it's a very powerful algorithm that can be used for many things. The very first thing, it can extract information from the data, so it's able to extract relevant dimensions of our feature space. So if I start with my original space of p dimensions, Rp, and now I compute my PCA subspace. Okay. I compute my PCA subspace. Right, so this is my subspace. What do I learn from this? Well, the very first thing that I can learn, right, is which dimensions, right here, I'm going to have this basis vector v1 and v2, right? v1 and v2 that define that hyperplane. These eigenvectors are nothing else than linear combinations of the original basis vectors, right? And what's a linear combination of the original basis vectors? Is nothing else than another vector, right, of coefficients that tell me how important or what contribution each original feature or dimension of Rp contributes to that eigenvector, right? So let's say that I have a three-dimensional space, and one dimension specifies my height, the other one my weight, and the other one my, I don't know, the amount of exercise, the hours of exercise a week, right? And I'm trying to find which of these are relevant with respect to some data set that I have of people that have developed certain specific disorders or illnesses, right? And I find these eigenvectors that say, well, they're all relevant, but the highest coefficients are for your height. And weird enough, but there may be a gene that's related to how tall you are that is also related to that illness, right? Okay? So that's already a very powerful way to extract and interpret information from data. This is where big data comes in. When you have huge amounts of data and you don't know what to do with it, right? You can use PCA to interpret what the data tells you that you should be paying attention to, right? Now, this is a double-edged sword. You have to be very careful. It's very powerful because it will discover relationships of your features and data that may give you really important results, scientific results, but it also has the problem that it's data dependent, right? So if something that is true is not represented in your data, then you will never find it, or you may find something that is not as good or as true as what you should have found. Worse, you could actually end up finding or representing something that's completely untrue. It happens to be true in your data, but it's not true in the biological or physical world, right? So you have to be very careful. Now, we tend to think, oh, data is unbiased, right? Data has no agenda. Well, data is always biased because do you know who collects data? People. And people, unfortunately, are biased, right? So why is one of our features the height of an individual? Because someone said, let's collect that data, right? And so on. The way we collect and store data is important. The variables that we compute and store are important, right? If we have data set that does not have the relevant information that we are interested in, there's no hope for PCA or any other machine learning algorithm for that matter to find it, right? So understand that there's this limitation. What other things can we find? We can find correlations of the data, right? So remember that we saw 3 examples in our last lecture. So one of them had points like this that were absolutely 100% correlated. We had a second case where the data points were the samples, meaning the samples were somewhat correlated, and a third case where the data points are not correlated, right? So they're almost uniformly distributed across the space. What happens here is that when I compute the eigenvectors of this, right, or the PCs, this PC is going to define that subspace that gives me perfect correlation from variable x to y. So f of x equals y. F, a linear function, right? And therefore, these are linearly correlated. This one is going to give me some correlation, right? But not perfect correlation. So these are going to be somewhat correlated, and these ones are not correlated at all, right? So if you compute this, you're probably going to end up with V1 here and V2 here, right? Basically, you haven't moved, right? Or maybe you've moved just a tiny bit, because it's usually the case that data are always correlated somehow, right? Maybe 0.001, but there is a tiny value there, right? Which is not considered correlation, obviously, it's just considered noise. But that is not going to move your basis vectors much, right? But here it is. Here you're going to have this V1 and V2. The difference between this V1 and V2 that I found here is that this lambda 2 is 0, right? And this lambda 2 is larger than 0, right? And that determines how much variance there is in the other dimension, right? So that allows me to find correlation. So I can find, if I plot, people, number of years that they've been smoking, and amount or degrees or size of the nodules in their lung CT scans, then I may find a strong correlation, right? May not be perfect correlation, but I may find a strong correlation, right? And that's very useful, obviously. That tells me more about the data. One other, there are many more applications. I'll do just one other of this. And obviously, we'll keep seeing applications of PCA because we'll be using it all the time. PCA can be used to do recognition, classification in machine learning. Okay, let's see that. And I'll do a very specific example called Eigenfaces. So again, we start with a set of images of faces that have been aligned. Remember that that's important. So we have a number of images of faces. Now these faces are defined by a number of pixels. And what I do, this is x1, this is xn. Each xi is written as xi1 through xip, p the number of pixels, right? So I take the first pixel, the intensity, the value of this pixel, right? The intensity of that pixel, and I write it here, okay? Now if you take computer vision image processing, you know that this is not called intensity, it's called luminance. But for what we care, let's call it either luminance or intensity, okay? The intensity of the pixel, the first one goes here. The second one, which is the one on its right, will go to xi2. The third one will be xi3, and so on. I go until the very end of the first row. Then I go to the first pixel of the second row, and I go row by row. This is called raster scan the image, right? So I convert this matrix into a vector. So I do that for all my images, and I end up with something like this. I have an RP feature space, and now I can compute the PCA space by keeping a percentage of the total variance. Okay? All right. Awesome. What the PCA space here, sometimes you will see this called the face space, because it defines faces, okay? What this means is that this hyperplane that I have found, that I have determined with the first PCs, right? So again, I compute sigma x. From here, I do an eigenvalue decomposition. I keep capital VR, which is V1 through VR, right? And these are the first R eigenvectors that define this hyperplane, right? Same as before. And now that face space, what it defines is the space within all space of all possible images that specify the vectors of faces, right? So let's go back to this. We already talked about this in, I think, last lecture. If I will start with the space RP, P the number of pixels in the image, then that space can represent every possible image you can ever take, right? Images of flowers, they are represented as a vector or vectors in that feature space. Images of cars are vectors in that feature space. Images of white walls, they are represented in that space, right? Any image you can ever take, an image of noise, complete just noise, that is going to be represented in that feature space, right? Images of faces are also going to be represented here. But obviously, they're not going to take the whole space. They're going to take a subspace of that space. That's what we're trying to find out. What is that subspace that represents faces? That's what PCA allows you to get, the subspace within that space that defines faces. Okay? So now you have your subspace in the original space of all images. So again, this can represent all images. But this red one can only represent faces. And now, let's say that you take another picture, right? I have another picture. I take another picture, and it gives me that vector right here in RP. And I want to know, is that picture the picture of a face? How could I know? Well, what I can do, I can orthographically project this onto my face space or PCA space, right? And now compute the distance between my original vector, this one, and my projected vector, right? That distance here tells me how far away my image is from an image of a face. If that distance is below some threshold, then I can consider, oh, yeah, that's most likely a face. Okay? See how this works? Now, you can do that for faces. You can do that for apples. You can do that for cars. You can do that for any object you want, right? And every time you end up with a different subspace, one for cars, one for houses, one for flowers, one for faces. And when you get a new image, you see which of the subspaces is closest to your image, and that closeness tells you the category of the object you're looking at. Right? Yeah? All right, excellent. Good. If any questions, that's the time, because it's your first project, so better get the questions out now. Now, getting back to eigenfaces or eigenflowers, if you use flowers. Now, these eigenvectors, you see this eigenvector right here, V1 and V2, that define this PCA space. You see that? Okay, these two eigenvectors. These two eigenvectors are defined in which space? In the original space of P dimensions, right? So these are eigenvectors of V1 through V1P. You agree? Now, I could, remember what I did here? I went from a matrix to a vector. I can now go from a vector to an image, right? Why would I ever want to do that? Well, let's think about this. If I do that, what am I going to get? I'm going to get low values, right, close to 0, where there is no correlation or no variance of the data in that dimension, right? So there's no variance in that normal direction of the plane, correct? And it's going to give me information, very high numbers, right? High numbers here of the variance that there are in other dimensions, right? this reconstruction of the eigenvectors, if you use it for faces, it's what's called eigenfaces. And if you use it for cars, you would call it eigencars and so on. Right? And when you plot them, well, you'll see in your project. Right? There's also, you have examples in the slides that I uploaded online, but you'll see they look like faces. Right? Well, not a surprise. They are faces, right? The eigenvectors define areas of the image that define a face. So therefore, it looks like a face. Right? Interestingly, also, if you use images with a variety of illuminations, the first 3 eigenvectors, or the 3 eigenfaces, actually define the different illuminations of that face, or faces in general. Now, if you've taken image processing with me, in image processing we talked about the illumination cone. You guys remember the illumination cone in image processing? And remember that it was 3-dimensional. And anyone may have wondered why it was 3-dimensional, right? And we explained the rank of the matrix and all this. Well, the first 3 eigenvectors are basically going to give you the illumination cone. Right? So if you move about these 3 first eigenvectors, you change the illumination of the image. Okay. All right, excellent. Now, there's one final problem that we need to address. Now, remember, if my data has been mean normalized, which you have to do, right? Because here I'm replotting this hyperplane in the place of the original feature space where it belongs to, after I have moved it with the mean, right? But first, I mean normalize the data because the eigenvectors are going to be computed, remember? Right here at the origin, right? That was the difference between the matrix Q that we compute when B was assumed to be 0, and then sigma x when B was different, oops, that was equal to 0. That was equal to 0, and that was different than 0. Remember that? And we said what that means is that the mean here is 0, and here the mean is not 0, right? So what we did to define sigma x, we subtract the mean, right? So if I have this definition, right? So I have the data mean normalized, then I can write this as x transpose, right? All right, so this matrix is P by N. Therefore, this product is going to be P by P. So I'm going to get the P by P matrix, right? Now, the images I uploaded online for you to work with for your project are not that large. We control P to make it a little easier on you. But if you take images these days with any camera, they're probably 10, 12, 14, 15 million pixels, right? So P is of the order of millions, right? So it means that your covariance matrix is going to be, say, 14 million by 14 million. And you can compute it, just, well, can you? Depends on the computer you have, right? But how about N? We have N here. N is most likely going to be in the hundreds, maybe thousands, right? K is in the best case scenario. I mean, in some cases you may have 1 million if you're very lucky, but it's rare that you have millions and millions of data points. So what you can do instead, you can compute, say, sigma x hat, which is x transpose x. And it turns out that if you now compute the eigenvectors and eigenvalues of this x hat matrix, sigma x hat, excuse me, then the eigenvalues of sigma x are actually equal to the eigenvalues of sigma x hat. And the eigenvectors of sigma x are proportional, not equal, but proportional to the eigenvectors of sigma x hat. Oops. So how proportionally exactly, and you'll need this to do your project. So as a first warm-up homework, I ask you to solve that problem to derive this result. And you're going to need to start with these two definitions of sigma x and sigma x hat. And then we'll call sigma x hat, for example, gamma equal lambda, whoops, not a, lambda tilde or hat, lambda hat gamma, right? And sigma x as before, v lambda v, right? And you have to see how you get to these two equalities. And obviously this is a function, that a linear function that you need to obtain in order to run that. All right, any questions? Yes, question.
Beside the PCA here, we use PCA to find a hyperplane to do classifications. But before that, the step is stack the element of the matrix and treat it as a vector and do the PCA and something. Do we lose some information to bringing the structure as a 2D matrix and treat it as a vector? Do we
Yes.
information on performance?
Yes and no. So you could treat it as a tensor. I don't think that we'll have time in this class to cover that. You could treat it as a tensor, and you can do PCA with tensors. It's not that complicated. So it's actually very practical, especially when you work with video. So because then you have an actual tensor of 3 dimensions, right? So not just tensor of 2 dimensions, which is a matrix. So you can do definitely PCA in matrices. I think, I'm not sure if this is right or not. I think it's called 2D PCA. It's been a while since I looked at this, but I think that there's an algorithm called 2D PCA or something like that that does exactly that. That you can look at. And then there are more general methods for PCA that can work with other tensors of higher order, like tensors of 3 dimensions that allows you to apply PCA in video, right? So absolutely. Now the good thing when you convert this into a vector, as long as you assume that this is in RP, and we talked that there are a lot of assumptions when you make this. But as long as you assume this, then know that every dimension is orthonormal to every other one, orthogonal rather, to every other one, right? Which means that it doesn't matter whether I go in this direction first, rows or columns, because this is orthogonal to this and to this and to this and to every other dimension, right? So, but what it is true is that you lose the structure of this. If there are correlations in the structure, you recover those. But if the information is encoded in some other way, you don't. We will see methods on how to find nonlinear correlations that may be embedded in the data, how to define these things with graphs to represent the spatial structure and other types of temporal structures. And when we get to regression methods, we will extend these methods also for other types of tensors, okay? Other questions? Okay, excellent. Now, correlations. So this allows us to find correlations, right? So in the project, I ask you to do the PCA classification, or classification based on PCA, and I give you 3 different data sets to work with. And I also ask you to build a classifier with the correlations, right? The correlations that you get in your correlation matrix, which you can extract from the covariance matrix, right? As we saw in class. Now, be very careful, because everything that we've defined thus far is based on how correlated different features are. Correlation is given by the data, not by the features. Remember, right? So if I have my data is faces, I'm going to find a certain number of correlations. If my images are of apples, I'm going to find a different set of correlations, right? And that's what allows us to use correlations for classification, because, or categorization rather, because different object categories give us different correlations. However, as you're always asked to repeat a million times, you should probably write this down on a wall and repeat it for the next 2 weeks every morning when you wake up. Correlation does not equal causation, right? Just because things are correlated doesn't mean that one causes the other, right? Or that one is the cause of the other. For example, in the US, the consumption, the amount of ice cream that is consumed correlates with crime rate, with the amount of crime that is perpetrated in the US. Now, I don't think anyone is thinking about banning ice cream with the hope that crime will go down, right? I mean, that would be silly, because everyone understands there has to be something weird here, something else that we're missing, because I don't think that when people eat ice cream, they become more criminal. They just find that this inner self that they have to commit a crime, right? What happens is that more crimes are committed when the temperatures are good, meaning, end of spring, summer, early fall. Guess when people consume ice cream? Well, usually at the same times. So obviously the two variables are highly correlated, but they are independent from one another. They're not the cause. One is not the cause of the other. Now, when we talk about graph theory, we'll explain how we can find this weirdness in our interpretation of correlations and causation, okay? And we'll talk about independence and conditional independence and things that are going to help us solve this. This type of correlations, like ice cream with crime, they're called spurious correlations. And you can define a spurious correlation, or let's say spurious correlation is when an observed variable shows or has a relationship with another variable which is due to some third unknown or unobserved variable. Right? So in our example, that would be the temperature. Right? The temperature is the unobserved variable that is hidden to us that actually creates a correlation between ice cream and crime. One way to extend PCA to try to address this is by a method called factor analysis. So let's talk about this because this is very important and it'll become extremely important when we talk about some types of deep learning as well. Factor analysis is very, very similar to PCA, but with an important difference, which is that we assume there is an unobserved latent space or set of latent variables. Let's call them Z of interest. Now, our observed variables, as before, are our x's, right? x1, x2 through xn. Our xi's, as before, we're going to say have p dimensions, so 1 through p. And we have our simple mean of the observed variables, mu. Now, let the dimensionality of the range space of Z be equal to k, okay? That means that there are k unknown random variables Zi or Zj. Let's call them Zj to differentiate them from Xi. So the range space of my latent variables, called the latent space, that is unobserved, that is hidden to me, right? I don't observe Z, I observe X. But my observations are somewhat related or somehow related to Z. Now, how are we going to model that relationship? Well, we'll have already seen a model to specify such a relationship. So for example, I can do X, my observations, minus the mean, right? So I'm going to mean normalize my data, equals WZ plus N. You remember that? So our last lecture, right? The simple linear model, which means our latent variables are mixed together, linearly combined, to generate our observations plus some random noise, right? So N, our noise, is assumed to be uncorrelated with our data and to have mean 0. Since the, yep, question.
Just real quick on some clarification. Let the dimension of, what is that?
The range space. The range space of Z.
All right, thank you.
Sure. So since W is the mixing matrix, the columns of W define the correlations of the observed variables X, right? How correlate they are. They are defined by this matrix W. These are called the factor loadings. Now, some models, when you work with this, sometimes people will assume that the expected value of Z is 0, right? So that the data is also mean normalized. So it is typical to assume that the expected value of Z is 0, and actually that the covariance matrix, right, of Z is also 0. That's very common to assume. I'm sorry, 0. It's equal to the identity matrix. Okay. Now we already know how to convert a non-identity matrix, covariance matrix, into one, right? The eigenvalue decomposition precisely gives us that, right? Applying eigenvalue decomposition actually linearizes or diagonalizes the matrix, right? And then multiplying by the inverse of the eigenvalues makes it the identity matrix, right? So if we combine this with the assumptions that we've made here of uncorrelated noise and latent variables, we could write that our covariance matrix, which of course given that model would be WZ plus N, that is equal to the covariance matrix of WZ plus N, which you can write as the covariance matrix of W plus the covariance matrix of N, right? Which is nothing else than W transpose plus a matrix phi, whose diagonal elements, right? So diagonal matrix whose diagonal elements are nothing else than the noise values, right? Or the noise variables. Similarly, we can write the conditional probability of X given Z, right? So that is what we observe given our latent variables. It's equal to the probability of X given our model, right? WZ plus mu, our mean, and our matrix of the noise variables. Here, I'm not going to get into the details yet because we'll get back to this later in the course, but here we assume that x1 through xn are independent, okay? Now, if we're going to use these models, then using maximum likelihood, we can compute the estimators of Z, the mean, and the covariance matrix, right? So if you do that, I'm not going like what we did with the mean and the variance and covariance matrix for our X before. If you were to do that, you are going to get that the expected value of Zi is matrix G W transpose phi inverse times Xn or Xi minus the x bar, meaning the sample mean, and that the covariance matrix it's equal to G plus the expected value of Zi times the expected value of Zi transpose, where G where G is equal to the identity matrix plus W transpose phi inverse W inverse. So factor analysis is nothing else than a combination of the things that we have seen in the last couple lectures. It is the same as PCA, but instead of now being interested on the correlations and the analysis of my observation X, observation of observable variables X, I'm interested in some latent variables that are hidden to me. They are very important, like the temperature, right? That is the one that really determines whether people commit crimes and eat ice cream, right? I'm very interested in finding that, but they are unobservable, and I have to define them somehow. This is how I'm going to define them. I'm going to use this linear model that we have seen before to define it, right? With the assumptions that we made before that tell me that I can assume uncorrelatedness for the noise, and I can compute, therefore, the covariance matrix of my actual observable data, and I can compute with maximum likelihood the expected values of Zi and the covariance matrix. Now, how you actually achieve this in practice, we don't have enough knowledge yet to do that. We need to know more about distributions and the PDFs, and we need to know about an algorithm that's called the EM algorithm for expectation maximization that's going to allow us to actually work this out, these actual equations, okay? And that we'll do in a few weeks. All right, it's about time, so we'll pick it up from here next week. Have a good weekend.